So let me just say one thing about, we have 4 more classes in the course. So what we're going to cover, the following, the syllabus for the next 2 weeks is in the book of Logan, chapter 4, sections 1 and 2, which is on separation of variables. So that is our preview of coming attractions. But the first thing we're going to do is go over the solutions to the second exam. So problem number 1 was to compute the convolution of 2 functions. F of t is equal to t, and g of t is the sine of t. So the convolution f star g of t is the integral from 0 to t. This is just the definition of convolution. F of t minus x g of x dx, which for us is the integral from 0 to t minus x times the sine of x dx. So this is the integral from 0 to t of t sine x dx minus the integral from 0 to t of x sine x dx. The integral of the sine is minus the cosine. So this is t times minus cosine x evaluated from 0 to t. And you do the integral of x sine x, that's integration by parts. So this is minus x cosine x evaluated from 0 to t, plus the integral of the cosine from 0 to t. So you do the little bit of calculus that you need to do. So this is minus t cosine t, or minus t if you like. This is minus cosine t minus cosine 0. So that's 1 minus cosine t. Trying to find a pretty way to do this. So minus t times cosine t minus 1. When you evaluate this, this is plus t cosine t. And this, when x equals 0, is 0. And this is minus the integral of the cosine, which is minus the sine evaluated from 0 to t. So that's minus sine t. So, and we get some cancellation. Minus t cosine t cancels this. So we get 1 minus sine t. Sorry, we get t minus sine t. All right. Just 1 second. Okay, so what we have is minus t cosine t plus t cosine t, they cancel. Minus t is plus t minus sine t. So that's the convolution. So as I'm going through these, if there are any questions, just interrupt me. Unmute yourself and ask me a question. Otherwise, I won't know if you have a question. So we have f star g of t is t minus sine t. And the Laplace transform of f star g, well, the Laplace transform of a convolution, you can do it directly, or the Laplace transform of a convolution is the product of the Laplace transforms. Laplace transform of t times the Laplace transform of sine of t. Laplace transform of t is 1 over s squared, and the Laplace transform of sine of t is what? Well, you're always allowed to look it up in the table. One over s squared plus 1. That's what it is. You could also have said that the Laplace transform of f star g is the Laplace transform of t minus sine t. That's the Laplace transform of t minus the Laplace transform of sine of t. This is equal to 1 over s squared minus 1 over s squared plus 1. But if you put them over a common denominator, you get exactly the same thing. So either form of the answer is perfectly fine. Okay. Any questions about that? No. Okay. Next problem. Just 1 second. Okay. Problem 2 is to use the definition of the Laplace transform to calculate the Laplace transform of the hyperbolic cosine. So the Laplace transform of any function f of t is the integral from 0 to infinity f of t e to the minus st dt. So that's some function.
Professor, sorry, yeah. Professor. Yeah, what is the cos? I never tried that. What is the difference between cosine and cos? What is that?
They're different functions. This is the definition of the hyperbolic cosine. That's all you need to know. This is the function. It just has a name. It's not connected to the ordinary cosine. So all you need to know is this is the definition of the function. That's all you need to know. Now, the way the ordinary sine and the cosine are related to the circle, the hyperbolic sine and the hyperbolic cosine are related to the hyperbola. But that's a separate lecture in calculus, and it's nothing that we need to know here. Here we just need to calculate the Laplace transform. So the Laplace transform of this hyperbolic cosine, this is the integral from 0 to t of e to the t plus e to the minus t over 2, e to the minus st dt. So this is, you can take out the 1/2 and write this as a sum of two integrals. So this is 1/2. The integral from 0 to infinity. This is t minus st, which is the same as minus s minus 1t dt. Right? This is minus st plus t plus 1/2 the integral from 0 to infinity e to the minus s plus 1 times t. So when you integrate this, you get minus 1 over s minus 1 times e to the minus s minus 1t, evaluated from t going from 0 to infinity, plus 1/2, 1 over minus s plus 1, e to the minus s plus 1t, from t going from 0 to infinity. At infinity, this goes to 0, so this is, s has to be bigger than 1 and bigger than minus 1. So what you get is 1/2, 1 over s minus 1, plus 1/2, 1 over s plus 1. So that's 1/2, 1 over s minus 1, plus 1 over s plus 1. And if you put it over a common denominator of s squared minus 1, you get s plus 1 plus s minus 1 is 2s. The 2 cancels the 2, and you just get an s here. So that's the calculation of the Laplace transform. Okay. Any questions about that?
So the concept of hyperbolic function, this is just an expression, a mathematical expression, right? The cos, whatever, I don't know the definition.
Yeah, it's just the hyperbolic cosine or cosh is e to the t plus e to the minus t over 2. That's all you need to know. You don't need to know the name. I mean, I could have just said, find the hyperbolic transform, find the Laplace transform of e to the t plus e to the minus t over 2. In fact, that's what I did. That's all you're doing.
Thank you.
Okay, let's see. What is problem 3? Use the Laplace transform to solve the ordinary differential equation u prime plus 3u equals t with the initial condition that u of 0 is equal to 1. So the Laplace transform of u prime plus 3u, that's the Laplace transform of u prime plus 3 times the Laplace transform of u. I write L of u of s to be just capital U of s. this is equal to S U of S minus U of 0 plus 3 U of S. So this is S plus 3 times the Laplace transform minus 1. And this is equal to the Laplace transform of t, which is 1 over s squared. So we have that the function u of s, we have s plus 3 u of s is equal to 1 plus 1 over s squared. So u of s is 1 over s plus 3 plus 1 over s squared times s plus 3. That's the Laplace transform. And then we need to find the inverse of the Laplace transform. What is the function whose Laplace transform is equal to this? Well, 1 over s plus 3 that's not so hard to find, but for this, the best thing to do is to expand this in partial fractions. So 1 over s squared times s plus 3 is going to be equal to something of the form a over s plus b over s squared plus c over s plus 3. And we have to find the a, b, and c. So if you cross multiply, you get 1 is as times s plus 3 plus b times s plus 3 plus c s squared. And for example, if you let s equal 0, you get 1 is equal to 0 plus 3b plus 0. So b is equal to a third. If you let s equal minus 3, you get 1 equals 0 plus 0 plus 9c. So c is a ninth. And you can find what a is equal to 2 by picking some other value for s. I don't know that it matters too much. Let's try. Suppose I let s equal to 1. I get 1 is equal to a times s times s plus 3. That's 1 times 4. That's 4a plus 4b plus c. But I know b and c. This is 4a plus 4b is 4 thirds plus c, which is 1/9. So this is 4a plus 13 over 9 equals 1. So I'll just do my little side calculation. So 4a is 1 minus 13 over 9, which is minus 4 over 9. So a is equal to minus a ninth. Good. So let's go back to u of s. U of s is 1 over s plus 3 plus 1 over s squared times s plus 3. So that's 1 over s plus 3 plus a over s minus 1/9 times 1 over s plus b over s squared. B is a third, 1 over s squared, plus c, that's 1/9 over s plus 3. So I have what? I have 1 over s plus 3 plus 1/9. Let's see. I have minus 1 over 9 times 1 over s plus 1 over 3 times 1 over s squared. And 1 over s plus 3 plus 10, 9, 1/9, that's 10 over 9, 1 over s plus 3. So it follows that u of t is what? So the inverse Laplace transform of 1 over s is 1. So this is minus 1/9. The inverse Laplace transform of 1 over s squared is t. This is 1/3 t. The inverse Laplace transform of 1 over s plus 3 is e to the minus 3t. So that's the answer. And let's check. So u sub t plus 3u is what? If I differentiate this with respect to t, I get 1/3 minus 3 10/9 e to the minus 3t plus 3u. So that's 3 times minus 1/9. That's minus 1/3 plus 3 times 1/3 t plus t plus 3 times this, 10/3 e to the minus 3t. So the plus 1/3 and the minus 1/3 cancel. This is minus 10 over 3 plus 10 over 3. These cancel. I'm just left with this equals t. So the differential equation is satisfied, and u at 0 is minus 1/9 plus 1/3 times 0 plus 10/9 e to the 0. So that's minus 1/9 plus 10/9 is 9 over 9 is 1. So everything checks. So it's always good to check, and we check, and the initial condition is satisfied as well as the differential equation. Okay. Any questions about that? Okay, if not, we go on to number 4, which is to use the Laplace transform to solve the partial differential equation ut plus ux equals x for x greater than 0, t greater than 0, with the initial condition that u of x0 is 1, and the boundary condition u of 0t is 0. So when we take our Laplace transforms, we get the Laplace transform of ut plus ux, which is the Laplace transform of ut plus the Laplace transform of ux, is the Laplace transform of x, which is x times the Laplace transform of 1, because we're integrating with respect to t. The Laplace transform of u with respect to t is what? This is s, capital U of xs, minus u of x0 plus, and this is the derivative with respect to x of u of xs, equals x times the Laplace transform of 1, which is 1 over s. So what we get is, for this function, the Laplace transform, so u is u of xs, du dx plus su is equal to, what is u of x0? It's 1. 1 plus x over s. And so this is just an ordinary differential equation to solve. If we multiply by e to the sx, we get 1 plus x over s e to the xs. And on the left-hand side, this is just the derivative with respect to x of e to the sx u equals this. X e to the xs over s plus e to the xs. So when we integrate with respect to x, is what? The integral of this, well, you have to integrate by parts. And when you integrate by parts, what you get is you have x e to the xs, 1 over s e to the xs. You have x over s e to the xs minus the integral of e to the xs, which gives us a 1 over s squared e to the xs. So this is equal to x over s squared minus 1 over s squared times s minus 1 over s cubed e to the xs, plus a constant. If I divide by e to the sx, I get u of xs is equal to x over s squared minus 1 over s cubed plus c e to the minus xx. Oops, I forgot a term. Oh, sorry. So, so when I integrate this, I get this, and then I also get the integral of this with respect to x, which is plus 1 over s e to the xs. I get a plus 1 over s there. So I have x over s squared minus 1 over s cubed plus 1 over s plus c e to the minus xs. So u of x comma s is x over s squared minus 1 over s cubed plus 1 over s plus c e to the minus sx. But I also know that u of 0t is equal to 0. So that means that capital U of 0s, this is the integral from 0 to infinity, u of 0t e to the minus st dt is going to be 0. So when I plug in x equals 0, I get 0 here. Capital U of 0s is equal to 0 minus 1 over s cubed plus 1 over s plus c, which means c is equal to 1 over s cubed minus 1 over s. So u of xs is equal to x over s squared minus 1 over s cubed plus 1 over s plus 1 over s cubed e to the minus sx minus 1 over s e to the minus sx. So that's the Laplace transform of u. So we now look for the inverse Laplace transform. the Laplace transform of t is 1 over s squared. So x over s squared is the Laplace transform of xt. One over s cubed. Well, what is that? Laplace transform of t squared is two over s cubed. So this is really, I can write this as minus, instead of 1, I'll write this a half, 2 over s cubed. I get minus 1/2 t squared. Laplace transform of 1 over s is 1. What are the Laplace transforms of these? Well, they're going to involve the Heaviside function. If you look at the Laplace transform of a function times e to the minus at, that is the Laplace transform of t minus x. And what's the Laplace transform of 1 over s cubed? We already saw that. That's a half t minus x squared minus h of t minus x. The Laplace transform of 1 over s is 1. Just 1 times 1. So this is our presumptive solution. Let's try and check whether this is correct. If t is less than x, h of t minus x is 0. And so u of xt is just equal to xt minus a half t squared plus 1. And in that case, because h, this Heaviside function, is 0 for negative numbers and 1 for non-negative numbers. So if t is less than x, t minus x is negative. So u sub x, u sub t plus u sub x is differentiate with respect to t. I get x minus t. Differentiate with respect to x, I get t. So I get x. That's the differential equation I had to satisfy. If t is greater than or equal to x, so t minus x is greater than or equal to 0, h of t minus x is 1. So ut plus ux, when I differentiate with respect to t, I get x minus t. This is 1. I get derivative of this with respect to t is a half times 2 t minus x. And when I differentiate with respect to t, this is just 0. This is just 1. Plus the derivative with respect to x. The derivative with respect to x, this is t. When I differentiate this with respect to x, I get a half times 2 times t minus x times minus 1. So that's minus t minus x. These cancel. These cancel. I'm just left with x. So if you carefully check, the differential equation is satisfied. And what about the initial condition? Let's see, what was the initial condition? Let me go back and the initial condition was u of x, when t is 0, you get 1. So when t is 0, this is 0. When t is 0, you get, sorry, when t is 0 and x is greater than 0, u of x 0. When you let t equal 0, you get, you get 0, 0, 1. Zero, zero, you get 1. And when x is 0, you get minus a half t squared plus 1. Plus a half t squared minus 1. Everything cancels. So the initial conditions are satisfied, but it does require a little bit of careful checking using the properties of the Heaviside function. Okay. Any questions about this? Okay. So problems 5 and 6 use what I call the method of coordinates, but I meant, of course, the method of characteristics, certainly not the Laplace transform. We want to use the method of coordinates to solve the partial differential equation u sub t plus 4t cubed x u sub x equals 0. This is for all x positive t, and the initial condition is that u of x 0 at time 0 is equal to e to the x. So we look at this function, this coordinate, and we want to solve the ordinary differential equation dx dt equals 4t cubed x with some initial condition x of 0 is equal to x naught. So this equation is separable. You get 1 over x dx dt is 4t cubed, or the integral of 1 over x dx is the integral of 4t cubed dt. This is t to the 4th plus a constant, and this is log x. So we get that x of t is equal to some constant times e to the t over 4. And x of 0 is the constant, that's x naught. So x of t is x naught e to the t over 4.
I don't know that one.
Okay. So u at x of t comma t is constant. So u at x of t comma t doesn't vary with t. So if you let t equal 0, you get u of x naught 0. What's the initial condition? The initial condition was x squared equals x naught squared. What is x naught? X naught is x e to the minus t to the 4th squared. So this is equal to x squared e to the minus 2t to the 4th. When you square e to the t to the 4th, you don't get t to the 8th, you get e to the 2t to the 4th. So this is the presumptive solution. Let's check. If I differentiate this with respect to t, I get x squared. The derivative of this with respect to t, I get a minus eight t cubed x squared e to the minus 2 to the fourth. If I differentiate this with respect to x, I get 2x e to the minus 2 to the fourth. If I multiply this by 4t cubed, this is exactly 8t cubed x. So u sub t plus 4t cubed u sub x, they cancel and I get 0. And in this, if I let u of x, if I let t equal 0, u of x comma 0 is x squared e to the 0, which is x squared. So the initial condition is satisfied. Okay. So this was using the method of characteristics or coordinates to solve a homogeneous partial differential equation. And the last problem was a non-homogeneous equation. It was the following. This is number 6. We have u sub t plus 3 t squared u sub x is cosine t with the initial condition that at time 0, u of x 0 is equal to e to the x. So this is what I'm multiplying u sub x by. I want to look at the differential equation dx dt equals 3t squared, x of 0 equals some number x naught, and the integral of 3t squared is just t cubed, and at 0, I have to get x naught. So x of t is t cubed plus x naught. And the derivative of u of x of t comma t with respect to t is u sub t plus 3t squared u sub x, which is cosine t. So u of x of t comma t, when I integrate that, I get sine t plus a constant. And when t equals 0, I get sine 0, which is 0, plus the constant. But u of x naught comma 0, this is e to the x naught. And x naught is x minus t cubed. That's my c. So u of xt is sine t plus e to the x minus t cubed. Again, let's check. ut plus 3t squared ux is equal to what? When I differentiate with respect to t, I get cosine t minus 3t squared e to the x minus t cubed plus 3t squared times the derivative of this with respect to x is e to the x minus t cubed. And these cancel, and I get cosine t. So my differential equation is satisfied. And u of x comma 0, when t is 0, this is sine 0 plus e to the x minus 0. This is 0. This is just e to the x. So everything checks. Ooh, good. Any questions about the exam? Okay. So we're studying in the book of Logan, chapters 3 and 4, though in 4 it's really just 4.1 and 4.2. So I went over very quickly chapter 3 before the Thanksgiving break. And there's some homework problems for tomorrow, but I'm happy to answer any questions about that right now. And then go on to talk a little bit about separation of variables. Okay. So we covered this a little bit much earlier in the term using Farlow's book, but I want to spend really the last 2 weeks going through this with a little bit more detail following Logan. So this is chapter 4, section 4.1, which is on separation of variables. And this is in a sense review, but review is important. And Logan, like Farlow, begins with the boundary value problem for heat conduction. So we have the differential equation U sub t equals uxx. Right? So you have a function of a time variable t and a space variable x, and the domain is bounded. That is, x doesn't go from minus infinity to plus infinity or from 0 to infinity. We have a bounded domain. Bounded domain for x. T is unbounded. When we have the initial condition, let's start with the boundary condition. We have the boundary condition that at the endpoints, x equals 0 and x equal pi, this is equal to 0 for all t. So this is the boundary condition. And we have some unspecified yet initial condition that at time 0 and position x between 0 and pi, u of x0 is some function f of x. So using the notation that Logan is going to use, we assume, right? We don't know this is true in any particular case, but you make this assumption, and if it leads to a solution, then you win. If not, you're stuck with trying something else. But we assume that this function u of xt is actually a product of a function of x, y of x, and a function of t, which we call g of t. So if you plug this into the partial differential equation, if u of xt is this, what is u sub t? U sub t is y of x times g prime of t. And uxx, the second derivative of u with respect to x, is the second derivative of y with respect to x times g of t. So our differential equation, ut equals uxx, becomes y of t g prime of t equals y of x g prime of t equals y double prime of x g of t. And the boundary condition is u of 0 t, when you let x equal 0, is y of 0 g of t is 0, and u of, at the other endpoint, the other boundary point, pi t, is y of pi g of t is also equal to 0. Now, notice that if g of t equals 0 for all t, then u of xt is 0 for all x and t, and there's really nothing to say. The only solution is the trivial solution, and in particular, u of x 0, which is f of x, has to be identically 0. So if g of t is 0, there's nothing. I mean, it's just a trivial solution. So we can assume g of t is not 0. And if it's not 0, you can, if g of t is not 0, what does that say about the boundary conditions? G of t is 0 for all t. Y of 0 is 0. And y of pi is 0. And
Professor,
yep.
from the boundary conditions between 0 and pi, you referring to one cycle?
No, the boundary means the value at 0 and at pi. It doesn't say anything about the value between 0 and pi. The boundary condition tells you what the value of the function is at the two ends, 0 and pi, for all t. And then there's an initial condition which tells you about t equals 0. But the boundary condition itself has nothing to do with x strictly between 0 and pi.
Okay.
So remember, when we assumed that u of xt separated into a function of x times a function of t, we had the differential equation y of x g prime of t equals y double prime of x g of t. If you rewrite that as g prime of t over g of t equals y prime of x over y of x, what does that say? Well, it says that if you fix x and let t vary, it can't change because it always has to be equal to whatever particular value you have for x. And if you fix t and let x vary, this doesn't really change. So that says that this has to be a constant. And I'm going to write this as minus lambda, even though lambda could be positive, negative, or zero, but that's just a convention that we start with. So we have, this is a second derivative. And we had the initial conditions that y of 0 equals y of pi equals 0. So now we have two ordinary differential equations. The simplest is that g prime of t is lambda g of t. So up to a constant g of t is e to the lambda t. Sorry, e to the minus lambda t. And we also have y double prime of x is minus lambda y of x.
Professor, the last step, do you use the integrating factor because you
From
answer
here to
the
here?
rate?
Is this what you're
Yeah,
asking about?
right. You use the answer derivative. The reason is e to the minus lambda t. This is the reason.
You don't need an integrating factor. This is just calculus 1, right? That is, the only solution of this differential equation is e to the minus lambda t, right? You know, if dy dt, or, I mean, in Calc 1, you learned if dy dx is some constant times x, then y is e to the minus lambda x. That's all. So, I mean, this is just, from calculus. You don't need any ordinary differential equations to know that. So for the function g, a solution is e to the minus lambda t times any constant, but I'm not bothering to put in a constant here now. I could. And for the function y, it satisfies this second order linear differential equation. And this one we also know very well. You don't need a course in OD, in ordinary differential equations, to know this. So let's look at different cases. So case 1 is, let's say lambda is negative. So lambda is minus some alpha squared. So minus lambda is plus alpha squared, where alpha is positive, and you get y double prime equals alpha squared y of x. Y. And we know the general solution of this is y of x is a e to the alpha x plus b e to the minus alpha x. Now, in that case, what do the initial conditions say? So y of 0 is a plus b is 0. And y of pi is a e to the alpha pi plus b e to the minus alpha pi. But of course, from the first equation, b is equal to minus a. So this is a e to the alpha pi minus a e to the minus alpha pi, which is a e to the alpha pi minus e to the minus alpha pi. Or I can write this, if you like, as a, factor out a e to the minus alpha pi e to the 2 alpha pi minus 1. And that is equal to 0. Y of pi is 0. So if a is different from 0, then this is 0. So e to the 2 alpha pi is equal to 1, which can only happen as alpha is equal to 0, which isn't correct. Alpha is positive. So we have a and b equal to 0, which means that y of x is the 0 solution, and we're looking for a non-trivial solution. So this case is impossible. So you can't have lambda less than 0. Case 2, when you have y double prime of x is minus lambda y of x, and y of 0 equals y of pi is equal to 0. Suppose lambda is 0. Then y double prime of x is 0, which means y of x is a linear function. So y of 0 is b is equal to 0. So y of x is ax. But y of pi is a times pi is also 0, which means a equals 0, which means y of x is identically 0, which is also no good. So we have to have, in order to have a non-zero solution, it must be the case that lambda is strictly greater than 0. It's positive. So if you have y double prime equals minus lambda y, with lambda positive, so lambda equal alpha squared, the only possible solution, the general solution, is a linear combination of trig functions. And what happens in that case? Well, check the initial conditions. Y of 0 is a cosine 0 plus b sine 0. This is 1 and this is 0. This is a is 0. So a is 0. So y of x is b sine alpha x. And y of pi is b sine of alpha times pi. This also has to equal 0. If b is not 0, which has to be the case if there's a non-zero solution, then sine of alpha pi is 0, which means alpha is an integer. The only values of the sine, which are 0, are multiples of pi. So lambda has to be the square of an integer. So when we go back to our diffusion equation, u sub t equal u xx, where u of xt is y of x g of t. We know that g of t is e to the minus lambda t. E to the minus n squared t. And y of x is b sine nt. I'm sorry, x. depending on n. So one solution of this equation for any integer, positive integer n, is e to the minus n squared t sine of nx. Right? So this is exactly the problem we solved in essentially the same way a bit ago. And the question is, so if you have one solution of this equation, any finite sum b sub n e to the minus n squared t sine nx, and goes from 1 up to whatever, this is a solution. And the question is whether, if you take some convergent infinite series of these, you get something which satisfies not just the boundary condition, but the initial condition. So at t equals 0, u of x comma 0, which is some function f of x, is summation n goes from 1 to infinity. When t is 0, this is 1, b sub n sine nx. So this is, as we saw before, a sine Fourier series. And we have, and we'll have some more examples where we try to represent a function in terms of these sines and cosines. Okay. All right.
You
So this
said
is
the
kind of
sine expansion.
what?
Sine
Okay.
expansion.
Sorry, what is strange?
No, I mean this is the sine expansion.
Oh, sine expansion.
Right.
Yeah, right. That's what it is. Okay. All right. I don't want to rush too far ahead because I think there's a homework assignment due tomorrow on problems on orthogonal series and various relations and about functions from chapter 3 of Logan. So
Oh,
what I'm going to
Professor.
do, I think is,
So
go ahead.
yeah. You can add cosine in that formula
In
for a
this
complete.
formula, no, well, in this particular problem, no. So we proved that the only non-zero solutions involve the sine function, but not the cosine function. That was part of the argument. So let's go back a step. In the case, so we have this differential equation, y double prime is minus lambda y, and we're in the case where lambda is positive, say equal to alpha squared for some alpha. So y double prime minus alpha squared y, the general solution to this second order linear homogeneous differential equation is a cosine alpha x plus b sine alpha x. But then we have the initial condition that at x equals 0, y of 0 is equal to 0. When you plug in x equals 0, you get a cosine 0 plus b sine 0, but sine 0 is 0. So you get a. So y of 0 is a, but y of 0 is 0. So a is equal to 0. So this term disappears. You only can have a sine function. So the condition that y of 0 equals 0 says this is a sine function. The second initial condition that y of pi is equal to 0 says alpha has to be an integer. Okay. So really spend a lot of time doing problems in section 3, and there'll be the next assignment will be from chapter 4. Sorry, chapter 4. And I'd like to spend a lot of time on Wednesday going over some of the homework problems from chapter 3 on orthogonal expansions. That's the secret. Okay, then that is it for today. Hope everyone is well, and we will be back on Wednesday.
Thank
Bye all.
you. Take care, Professor.